Chapter 2 is titled Reasoning and Proof. Reasoning and proof. We'll be talking about lots of different ways to reason, think through different types of problems, as well as prove things, prove what are called conjectures. In 2.1, we're going to use inductive reasoning. We'll learn what inductive reasoning is, how to make and think through a conjecture. We'll also talk about how we can disprove a conjecture using counterexamples. 2.1, use inductive reasoning. Example 1. The first two examples are going to have the same directions here. Describe the pattern that is given in numbers below, and then write the next three numbers in the pattern. So the first types of problems, we're trying to identify a pattern of some sort. And then we're going to use that pattern to continue the sequence of numbers. So the first one's not bad here. It's fairly basic. We are given -4, -12, -36, -108. Again, -4, -12, -36, -108. So first thing I'd notice is our numbers are becoming more and more negative, and pretty quickly, not by a consistent amount. Next thing you would maybe try is there something I can multiply by to go from here to here? Well, that's times 3, and -12 times 3, and -36 times 3 does give us -108. We are multiplying by a positive number because all the numbers are indeed negative. So there's our pattern. Describe the pattern, multiply by 3. And write the next three numbers in the pattern. So 108 times 3 is 324. Times 3 is what? -972, I think. Yeah. And 972 times 3 is -2916. So easy enough. Sometimes the patterns are very basic. Just adding a number over and over again, subtracting it, maybe multiplying, maybe dividing. Example 2, we're again given a number sequence. Exactly the same directions. Describe the pattern that's given numbers, and then write the next three numbers in the pattern. This one's not as obvious though. 6, 12, 25, 24, 48, 25, ... 6, 12, 25, 24, 48, 25. I want you to pause the video and think through what our pattern here is, as well as what the next three numbers would be. Pause it, think about it for a minute or two, maybe talk to a partner about it, see if you can figure it out. We actually have a couple different patterns going on at the same time here. First thing I do is kind of, okay, +6, well, that doesn't work, and times 2. Times 2 doesn't give me 25. Here I go down by 1, and then I'm times 2 again. And then we're going down. Notice the number 25 is popping up every once in a while, right? It's right here. I've got two numbers and then a 25, two numbers and then a 25. So if I continue that pattern, I'd have 2 numbers and then a 25. So part of the pattern is every third number is 25. And then if we ignore the 25s, well, we said this is times 2, and this is times 2. And from 12 to 24, that's also times 2. So if we took the 25s out, it's just like the last one where it's just multiplying by the same number over and over again. So if we put that in, I've got 48 times 2 is 96. And 96 times 2 is 192. So we've got our other 2 numbers, or our other 3 numbers. Describe the pattern. Every third number is a 25. We put that. All other numbers double. Or times 2 for the remainder of the numbers. Something to that effect. So some patterns are very easy. Some require a little bit more work to think through. A couple more definitions here. The first being a conjecture. A conjecture is a statement that hasn't been proven that is based on observations. So when we make conjectures, we're going to observe something, and then we're going to come up with a statement that matches up with those observations. We're not going to need to prove it, at least not here in this section. But a conjecture, it's an unproven statement that is based on observations. If you've proven a conjecture, now it's called a proof. We'll talk about those a lot more moving forward. So we're going to make observations and then come up with a statement that matches with those observations. Inductive reasoning is when you find a pattern in specific cases and then write a conjecture about how that's going to work for the general case. So we look for patterns. We just talked through a couple number patterns, but we're going to look for patterns in specific cases. So we'll come up with a few small examples and then use that to write a conjecture for the overall general case. That entire method for coming up with a conjecture is called inductive reasoning. So example 3 says, given 7 collinear points, make a conjecture about the number of ways to connect different pairs of the points. So we've got 7 collinear points. Collinear means they all line up in a straight line. Seven collinear points. We are going to make a conjecture about the number of ways to connect different pairs of the points. I'll give you a minute to write there. So the number of ways these could connect, like I could connect these two. There's one way. I could connect these two. There's 2 ways. I could connect these 2. That's 3 ways. Or these 2 is 4 ways, and so on. How many different ways could I connect them? One thing you could do to figure that out is we could just draw them all in, right, and count how many there are. That wouldn't be making a conjecture, though. Remember, for a conjecture, we're going to use observations, we're going to use inductive reasoning here, look at a pattern in specific cases, and then use those observations to write our unproven statement. So let's look at specific cases. Let's start with one dot. If I just have one dot, so number of dots, 1, and ways to connect. How many different ways can I connect that one dot to the other dots? Well, there are no other dots. So if I just have one dot, there are 0 ways to connect. Now let's look at the specific case when I have 2 dots. If there are 2 dots, I can connect those 2 dots just one way. This one with that one right there. So 2 dots, I have one way. If there are 3 dots, for 3 dots, I have this one that I already did. I could connect these 2, there's 2. Or I could connect these 2 here. That's 3 different ways that we can connect 3 dots. How about if we have 4 dots? 4 dots. 1, 2, 3. The 3 I already had. That's 4, 5, 6, right? And I already connected these 2. So 6 different ways. All right, let's look at one more specific case. One more specific case with 5 dots. 1, 2, 3, 4, 5. Well, we already have those 5, or I'm sorry, those 6. 1, 2, 3, 4, 5, 6. And connect these 2, 7, 8, 9, 10. So we have a total of 10 different ways. So we want to come up with a conjecture on how this pattern is working and then use that for the specific case of 7. We don't want to have to go through and draw 7 and count them all up. We want to use our conjecture to figure out how many different ways there would be to connect the 7 dots. So with 1 dot, there's no ways. 2 has 1, 3 has 3, 4 has 6, 5 has 10. 5 has 10, yeah. Let's think through what our pattern is here. Well, this was +1, right? This is +2, +3, +4. So our conjecture is each time we add a dot, the number of new ways to connect increases by 1. So with 2 dots, I increased the number of ways to connect by 1. With 3 dots, the ways to connect, well, I only had 1 way. Now I have 2 new ways. Now I have 3 new ways. Now I have 4 new ways. So that's our conjecture. Remember, conjecture is unproven. We don't need to prove that in any way. But based on these observations, it sure seems as though this is correct. Then we can use that conjecture. If this continues, this would be 15 and this would be 21. 21 times with 7 dots. If you do think through why this pattern exists, notice if I add one more dot, well, I'd already have all these 10. So the number of new ones is just the number of ways I'm connecting this to these previous dots. And there's 5 of them, right? So I have 5 new ways. 1, 2, 3, 4, 5. So each time we add one, we are increasing this by that one. So that is what a conjecture is. That is inductive reasoning. Inductive reasoning, again, we come up with specific examples to come up with what we think a rule is, called a conjecture, and then use that conjecture to answer the question. One more definition here, it is a counterexample. A counterexample. A counterexample is a specific case for which the conjecture is false. It proves that a conjecture is false. All we need to do is come up with one counterexample. If I can come up with one counterexample, that proves the conjecture false. So example 4, we're asked to find a counterexample to disprove the following conjecture. Find a counterexample to disprove the conjecture below. And the conjecture that's given says the value of x squared is always greater than the value of x. The value of x squared is always greater than the value of x. So we need to come up with a counterexample. When we're doing that, especially when it deals with numbers, we want to kind of think through different types of numbers. So we're thinking about x and x squared. We need to come up with an example that shows that this isn't always true. Well, pick a number for x, 5. X squared is 25. Well, x squared is greater than x here. So that's not the counterexample we're looking for. We're trying to come up with something that proves that this is not always true. You could just keep guessing number 6, but usually when you want to keep guessing, you want to guess a number that's different in some way than the number that you just guessed. So we guessed a positive number, maybe -2. Guess a negative number. -2 squared gives us 4. Well, x squared, 4 is bigger than -2, so that one doesn't work either. We guessed a positive number. We guessed a negative number, maybe guess 0. 0 squared is 0. X squared is always greater than the value of x. It's not greater than the value of x here. They're equal. So there is a counterexample. Another good one, 1 would work. 1 squared is 1. If one's like that, maybe it said greater than or equal to, if it did say that. Well, now these would not be counterexamples in that case. Well, we guessed a positive, we guessed a negative, we guessed 0. Fractions sometimes work. 1/2 squared, 1/2 times 1/2 is 1/4. Notice 1/4 is not greater than 1/2. So this would be a counterexample, both to the original statement and if I added in the or equal to. That's it for the notes today. Reach out with any questions you might have.